Okay, so hello everyone. Welcome to my class. I'm Yang Wang. I'm an assistant professor at the Department of Chemical Environmental Materials Engineering at the University of Miami. And this semester, I'll be learning together with you about instruments that do aerosol measurements, aerosol and air quality measurements. Okay, so at the beginning, I'll just briefly introduce myself. So I joined the University of Miami in the summer of 2022. So I've been staying on campus for 1 year now. So before that, I got my bachelor's degree in thermal engineering. It's under the Greater Engineering School at Tsinghua University in 2012. And then I started my PhD study or graduate study at Washington University in St. Louis. And I got my degree in energy environmental chemical engineering in 2017. So after that, I did some postdoctoral research at Brookhaven National Lab on Long Island, which is more focused on the atmospheric aerosol measurement, field campaigns, and data analysis. So I joined Missouri University of Science and Technology as an assistant professor in 2019, and then I worked there for 3 years. And after that, here I am at the University of Miami. So in terms of my research is mainly focused on the aerosol and air quality measurement. So for example, this includes a project about the combustion aerosol measurement and combustion nanoparticle synthesis. So I also have a project about the long-term atmospheric aerosol data analysis, trying to look at the aerosol, cloud, and climate interactions. And during the COVID-19 pandemic, I became quite busy. That was because I remember at the beginning of the pandemic, there was a severe shortage of the qualified or certified masks. And at that time, the CDC gave us different kinds of recommendations for us to make the DIY masks. And this is especially an issue in Missouri S&T or Central Missouri, because there we don't have a lot of resources for these masks. And also there's a severe shortage of these masks because there's a major hospital located in Rolla, Missouri. So because of that, I remember basically Missouri ST gathered a special task force to try different types of materials and then to try to find out whether we can make masks with them, let different patients try them to check the fitting, but they need someone to do particle filtration measurements to test that these masks can actually work to filter out the particles. So I remember my department chair just knocked on my door or actually sent me an email asking, hey, Yang, do you have instruments to do particle filtration measurement? And I said, of course I have, right? Because I do aerosol measurement. And I have been testing these filtration systems since I started my graduate studies. So because of that, we did a series of research trying to find out what is the filtration performance of the common, let's say, household mask materials, and also how can we improve the performance of these materials. And after that, actually, this is a project that's mainly done by the PhD student in my group, Wei Hao. And remember, after we did these series of studies, we became wonder, well, wearing masks can only prevent, right? It can prevent the transmission of the disease. But what about the transmission of the disease itself? How is that related to aerosol properties? And for example, will the pathogens decay by themselves well after they are aerosolized? At least the people in the beginning of the pandemic believe that the transmission only happened in droplets, which means that they only happen in particles or aerosols larger than 5 micron. And if people stay for 6 feet apart or 2 meters apart, then we can be safe. Later, it turns out that it's not as simple as people thought, right? So because of that, we also started a series of studies on bioaerosols through the collaboration with a professor in biology. And there I learned quite a lot on these biological systems, bioaerosols. And then also looking into the airborne transmission of the diseases. So this is about my research. You can see they actually scattered in different topics, but overall, I'm very interested in the aerosol and air quality, both on the measurement side, but also the and also on the instrumentation side. Okay. So now let's get to the technical contents of this class. So this class is called aerosol instrumentation. But what is an aerosol? Okay. So for those of you who have taken Dr. Biswa's class on aerosol science and technology, you probably already discussed this question, right? So in his class, he probably called aerosol or define aerosol as a stable cluster of molecules, right? So it doesn't matter where the medium is. In that sense, even our Earth is an aerosol. But actually, you can apply a lot of these aerosol physics into these planets in planet systems or into our universe, right? But more specifically for our class, we're just going to focus on the aerosols that we deal with our daily life, okay? So in our sense, the aerosols are actually defined as solid or liquid particles that are suspended in the air, okay? So the word of aerosol come from the word of hydrosol. Actually, the hydrosol was defined in the beginning. So hydrosol is, based on the name, you can see that it's basically suspended in liquid, right? So they can be liquid or solid particles suspended in another liquid. So for example, the colloids is a perfect example of the hydrosol, right? So that's the definition of aerosol, and those are going to be the topic of our class. And then we have the question, what are the impacts of aerosols? Okay, so we know that the aerosols are encountered in our daily life, but how do they impact our daily life, right? What are the impacts? So the most obvious impact is on the air quality, right? Because we know basically the aerosols are also known as the particulate matter or PM. And the Environmental Protection Agency or the EPA have been doing these PM measurement for a very long time, right? So here I'm showing you a few pictures as a contrast to show how the PM or the aerosol concentration affects the visibility or affects our air quality. So here it's showing the photos of the Yosemite National Park, right? So you can see when the PM concentration is very low, 0.3 microgram per meter cubed, right? And you can really see far away. You get the pleasance, you get the pleasant feeling or pleasant mood when you go to a national park and get lucky and then see this clear weather or the clear air. But there can be some scenarios where the PM concentration can be quite high. For example, if there are, let's say, urban aerosols getting transported into here, or there can be wildfires, generate smoke, and then get transported into the national park, then under that situation, the PM 2.5 concentration can be pretty high, right? For example, when you get to around the 43.9 microgram per meter cubed, then you can see this hazy environment, hazy air, right? So also you see here, we have the definition of PM 2.5 and PM 10. So 2.5 and 10 here represents the size of the particles, right? PM 2.5 are basically aerosols with aerodynamic size below 2.5 micrometer, and PM 10 are aerosols with aerodynamic sizes below 10 micrometer, right? So which means that PM 10 is always going to be larger than PM 2.5, right? So here we show another two pictures of the Glacier National Park, right? So you can see when the concentration is low, then you have better visibility, but when the concentration is high, you start to see hazy environment. But you may wonder, well, here it's just 34 microgram per meter cubed as compared to Yosemite. Its concentration is actually lower, but why is it more hazy compared to Yosemite National Park? Okay, so it's more likely, most likely, because this is over a lake, right? If you have lake, Then when you have aerosols here, then the water vapor can actually grow onto these particles, making their size larger. If their size becomes larger, they scatter more light. Basically, they block more radiation or more visible radiation from the background, right? So in that case, you cannot see the scenes really well, right? So basically, the amount of water vapor that grows onto these particles will also affect the visibility. And in this case, this is related to the hygroscopic properties of these aerosols. I'm going to cover hygroscopicity later on too. Okay, so apart from the air quality, or basically the visibility, right? So the aerosols can also lead to quite significant health effects. So I would say this study is one of the earliest studies talking about how air quality or the aerosol concentration might affect the human health. Okay, so basically on the x-axis, this is showing the PM 2.5 concentration. On the y-axis, this is the adjusted mortality relative risk, right? So basically, this is the mortality that's associated with the aerosols. So here, different letters represents different cities. For example, P represent Portage, right? T represent Topeka, and then W is Watertown, right? L is St. Louis, H is Harriman, S is Steubenville, right? And then this is basically the data that's collected from different locations during different campaigns. And the upper and lower case represents different time periods, right? Or basically different measurement campaigns. So you can see there is a positive correlation between the PM 2.5 and the mortality relative risk, right? So nowadays, there are different types of studies trying to understand, let's say, this is an intercomparison of different cities, right? So there can be also comparison within that city, so which is more related to the, let's say, the social economic disparity within a city, right? For example, the poor region of urban area may be exposed to higher concentration of PM, and because of that, they may lead to higher mortality rate too, right? So basically, right now, I would say the understanding the correlation or the health impacts of the air pollutants is still an ongoing and a very hot topic, right? But overall, how does air pollutants affect human health? So here, this is a summary of the World Health Organization data, right? Showing all the different reasons or different burdens of different types of factors, right? So you can see when basically the high blood pressure is cause the largest global disease burden, right? So the next one is tobacco smoking, including secondhand smoke. And you see the third one is related to the air pollutants, right? That's the household air pollution from solid fuels. So different colors here represents different types of diseases, right? Here are the reasons or the factors that might lead to different types of disease. So the examples of disease can be cardiovascular disease or the respiratory disease and so on, right? But technically speaking, tobacco smoking and secondhand smoke is also related to air pollutants, right? You're generating particles, right? Tobacco burning will generate different types of hydrocarbon aerosols, and then some gaseous pollutants too. So then if you further look down, then you have this ambient particulate matter pollution, which is also causing a pretty high global disease burden. So overall, the air pollutants or the air pollution leads to around 7 million global deaths per year, right? And then that is around 10% of all the death numbers. And then from the statistical analysis of 2012, it shows that more than 200,000 deaths can actually be avoided if we improve the air quality. Okay, so furthermore, on the health aspect, as I introduced earlier in this class, right? So during the COVID-19 pandemic, there's also a significant focus on aerosol research, right? Because at the beginning, people are confused about how the disease is being transmitted. Many people believe that it is transmitted through droplets. So that's why at the beginning, we didn't even ask people to wear masks, right? We just need a separation, keep 2 meter. We have this 6 feet rule or a 2 meter rule, right? To just keep people staying apart from each other. But it turns out that actually 5 micron, 5 micrometer is not the appropriate boundary to tell the difference between the aerosols and the droplets, right? So by simple calculation of the particle drag force and basically through the physics equations, you can find out that the 5 micron particles can stay in the air for a sufficient long time, and then they can actually get dispersed way more than 2 meters, right? So some advanced or more recent calculation models actually find out that instead of 5 micron, 100 micron is a better boundary to tell the difference between aerosols and droplets. And in addition to the settling, when the particles are generated, for example, if there are, let's say, 5 microns when they're generated, then they can also evaporate. And their evaporate is pretty high. If you use the, let's say, the equation to predict the condensation and evaporation of the water vapor. Okay, so their size can also shrink, right? So basically they can change from a droplet into an aerosol, which eventually they are just a suspension of a liquid particle in the air, right? So technically we can call all of these respiratory particles as aerosols. There isn't such a thing to differentiate between droplet and aerosols. Okay, so this is also related to the health effects of the aerosols. And then the aerosols can also pose significant impact onto our climate. So especially on the climate aspect, people actually separate the climate impact into the direct effects and the indirect effect. So the direct effect directly means the scattering and absorption of the radiation. Okay, for example, if you look at this satellite image, this is showing the Southern Asia, right? So basically here is India, here is Bangladesh, right? So you can see there are some particles being generated, right? These are the aerosols being generated from potentially from the burning activities or pollution, industrial activities, right? So these aerosols actually, in terms of their color, they look lighter compared to the land surface or the ocean surface, right? Because the ocean looks darker, which means that it can absorb more radiation or more heat from the sun. The land is the same. And overall, the aerosols are, because they look lighter, right? They look wider, so they can reflect radiation back into the universe, which we'll call a net cooling effect of our Earth's climate, right? But it really depends on what type of aerosol we're talking about. If we're talking about black carbon aerosols, for example, just if you're directly burning coal under an incomplete burning condition, then you can generate a lot of soot, right? The black carbon. So black carbon is even darker than the ocean, right? So which means that it can actually absorb more heat. But overall, the aerosols that are generated from human activity are more reflective than the underlying surface, which means that they are going to cool the climate. Okay. And at the same time, if you see from this image, there may be, well, there may be some clouds here, right? The cloud is even lighter than the aerosols in terms of their scattering. But how are the clouds formed? The clouds are formed from aerosols, right? So basically, when you have aerosols being generated from different type of activities, it can be natural activities, for example, volcano or dust blowing, or for example, the sea salt, let's say over the ocean, there are ocean like sea salt sprays, right? So after you generate these aerosols, the air will rise up. When the air gets higher, what happens to the temperature? The temperature gets cooler, right? And at the same time, the water vapor is also brought up to the higher altitude, right? And then the relative humidity increases until it reaches supersaturation, which means that the water vapor is going to grow onto these aerosols, and then they become cloud droplets. After they become cloud droplets, their volume is larger, so they can eat up some of these aerosols, but more importantly, they can consume the water vapor in the air, right? When their size become sufficiently large enough, for example, in a range of 10 to 20 micrometer, then they can block the light and then become cloud, right? So you can see we form clouds just based on, well, there has to be aerosols in order to form clouds. And here I'm also listing the supersaturation range in the clouds. So normally the supersaturation is very low. It's between 0.05% to 2%, right? Which means that relative humidity is 100.05% to 102%, right? You just need a tiny little bit of supersaturation to create cloud droplets in these clouds. Okay, so well, some of you probably won't believe that. Well, you have so much clouds here. Are they all related to the aerosols? And as a matter of fact, it is, right? So here I should have a very short video, basically to prove that if there's no aerosols, then no clouds.
It's time to improve your writing game with
Let me share the screen again.
Day. There's no particles.
This is a video clip, right, in the polar region, right? People do all of these expeditions or experiments in the polar stations, right? So in the polar region, since there's no very, very few human activity, so there's no pollution. Basically, there's no anthropogenic emissions, right? And because of that, the air is very clean and you can't see any clouds, let's say in the sky or like the hazy condition, you won't be able to see that.
whatever. Just breathe, right?
Yeah, just breathe. So there's the particle concentration is 5 per cubic centimeter.
You ready?
Yep. Let's see. No breath. Try on the other side so the sun faces you. Yep. No breath. Minus how much? -8. You can't see it because there's no particles, no fog.
Nothing.
Nothing. Yeah. So, Kathy, would you just demonstrate that this is hot tea?
How do I demonstrate with this?
Because you put it inside, and if it starts diluting and changing color, that means it's hot. So there's no flow here.
So we have some hot tea here.
Hot tea here.
I'm about to stick some Earl Grey into this cup of hot water.
And there's hardly
any steam coming out.
because there's no particles.
Want to walk
Is
inside?
it-
Want to walk inside and show how much steam is coming out?
Sorry?
You want to go inside and show how much steam is coming out inside?
Yeah.
This water is really hot. Okay, so we're gonna walk inside, so you can see what it looks like. How much steam's actually coming out with non-really clean air.
Oh, I don't have a lighter. Do you have a lighter?
Yes, I do.
Oh, just put the lighter. Just come, Kathy.
Oh, okay.
Just put the lighter above the steam.
Instead of going inside, we're just gonna put a lighter over it. Look at that.
Oh my God.
Look at that.
Particles?
Particles. No particles.
No particles.
Why is this?
Particles.
Because lighters produce
particles.
huge amounts of very small particles.
Yeah, all right.
Yeah.
So the pollution from the lighter.
Pollution from the lighter causes
Okay.
the fog to be formed.
Great.
And just to prove that we are at the...
Can I drink this so I don't freeze?
So, to thank the demonstrators.
That was
Cheers.
nice
Yeah.
experiment.
Okay, so this is a very nice demonstration that how the aerosols may interact with water vapor and further lead to cloud formation, right? So similar phenomena that's happening in our daily life can be, for example, if you live in the northern state, or if you have been to the northern part during the winter, whenever you speak, you see the breath fog, right? You see the fog in front of you. The reason why you see that is because it's similar to what's shown in the video, right? The ambient environment is quite polluted. You have a lot of particles there, but the exhalation, the air that you exhale, contain a lot of water vapor, right? The RH, relative humidity, is almost 100% under a high temperature, because that's from your body, right? The temperature technically should be 37 degrees Celsius, right? Once they're exhaled into the air, the temperature cools down, and then you have supersaturation. Once you have supersaturation, then the water vapor can grow onto the existing aerosols in the air, right? That's how you see the breath fog, right? So this is kind of the indirect effect of the aerosols on climate. You form clouds, and then you lead to lead to a net cooling effect of our climate, right? This is a demonstration. So basically, when you have clouds, then you have the reflection, and then they can get reflected back into the universe, right? So this will lead to the net cooling effect. So another example to show the aerosol indirect effect is that sometimes when you see the satellite images, you'll see these larger scale clouds, right? That's covering the certain, let's say, ocean area or land area, right? This is because of synoptic scale processes. For example, you have a cold front, you have storm passing by, you'll see these larger scale clouds. But at the same time, you can see these narrower lines of clouds, right? They look a lot brighter. Basically, the number of aerosols or number of cloud droplets in there is higher, right? So they're more persistent clouds. Where are they coming from? Where do they come from? They're released by ships, right? The ships also generate these aerosols, right? These are basically ship tracks. When they pass by, then the aerosols get floated up, right? Water vapor grow onto them, then you form clouds. Okay, so in order to estimate how the human activities or the anthropogenic emissions influence our climate, so you know the IPCC, right? So the IPCC generate, let's say, annual assessment reports, right? Actually, it's not annual, right? And basically, there's assessment report each time before the IPCC conference. So basically, people have been generating these reports for the past almost 20 years. So this is the report that's coming from the AR4, right? This is summarizing how the human emissions is affecting the Earth climate for different types of constituents, different types of chemicals. For example, there can be these long-lived greenhouse gases. You have carbon dioxide, nitrogen. This is nitrous oxide, right? And then methane. So these, we know that they are global greenhouse gas species. So there can also be ozone, right? The ozone is also warming when they're in the troposphere, right? And then in terms of aerosols, right? So you can see that we separate them into the direct effect and indirect effect. So direct effect is the direct scattering and basically absorption of the light or the heat radiation, right? Indirect effect is the cloud formation. So you can also see the confidence in terms of how much it affects the radiative forcing. So basically, if there's no, or technically, theoretically, if there's no human activity, right, then from 1750 to 2005, then this the total value should be zero, close to zero, right? And because of the human activities, then you are going to increase, basically, to keep more radiative radiation, keep more radiation on the Earth, right? So this is going to keep or lead to a net warming effect, right? So basically, we can also see how much or how confident we are about these different effects, right? For example, carbon dioxide, we have high confidence, right? Scientific understanding, right? But in terms of the aerosols, especially the indirect effect of aerosols, you see we have relatively low understanding, right? Other relatively low confidence factors include the stratospheric water vapor from methane, right? And then linear contrails, right? So these are basically the aircraft emission, how that may lead to the cloud formation in the stratosphere and further lead to the climate effects, right? And there's also the solar irradiance. This is related to the sun activity, right? So to better understand the human activity onto our climate, I guess people need to put more efforts into these low confidence processes, right? So basically, here you can see if we summarize all of these, right? So basically you have these greenhouse gas species over here. It's causing a warming effect in radiative heat, radiative forcing. There can be aerosols that's causing a cooling effect. If you summarize both of these, then you're going to get a somewhat broader or uncertain radiative heating that's basically representative of the human anthropogenic activities, right? So this is AR4. This is, I think, in the meeting of 2006, right? And then as people's knowledge gets better and better, we can also minimize, or we can also reduce the uncertainty associated with these quantities. For example, in the AR5 report, right, in the fifth assessment report, so you can see, indeed, the uncertainty is getting smaller. For example, for the aerosol cloud interaction, this is indirect effect, right? So the green one here represents the AR4 estimates. So remember, it was here last time, and now it's getting, I mean, the uncertainty is getting smaller. But you can see the uncertainty is still very large. It's almost comparable to the absolute cooling effect, right? The same thing for the aerosol radiation interaction here. You have a pretty high uncertainty, right? So basically, you still have a relatively low confidence in terms of the aerosol properties, how the aerosols is influencing our Earth's climate. And then most recently, I think this is the IPCC meeting of 2001, right? So we have this AR6 coming up. So you can see the uncertainty of the aerosol cloud interaction is getting even smaller, but still we need to make improvement to understand how the aerosols may interact with our Earth's climate. So this is the impact of the aerosols onto our Earth's climate. But actually, other than posing an impact onto the human health, onto the air quality and the Earth's climate, the aerosols also place a huge impact on our daily life. Okay, so people normally think of aerosols as the posing negative impacts, because if there's no aerosols or no anthropogenic aerosols that are generated by human activity, then our air quality will be good, right? Then our climate won't be impacted by all of these emissions, right? So they tend to cut off the emissions. They tend to, and also try to remove the aerosols. But a lot of times we're also enjoying our life because of the benefits of these aerosols, right? And nowadays, people actually use the aerosol or the nanoparticles synthesized by the aerosol methods in almost all aspects of our daily life. And the most direct example is the sunscreen. Okay, so next time when you pull out a sunscreen, then try to look at the contents in there, right? And the ingredients in there. You also always see these zinc oxide nanoparticles or titanium dioxide nanoparticles. So people use these nanoparticles because they have very good light scattering properties, so they can reflect the solar radiation instead of absorbing the radiation, right? So, and these nanoparticles are actually made by the aerosol synthesis approaches. So what happens is that we introduce precursors into a furnace reactor or into a combustion reactor. Well, this is a flow reactor. So inside the flow reactor, you have the synthesis precursors going through nucleation, condensation, coagulation, and form these nanoparticles in large quantity. So they can be generated in, let's say, tens per hour, right? So we call these as commodity nanoparticles. And it turns out that nowadays, more than 60 or 70% of these commodity nanoparticles are made by these aerosol synthesis systems, right? So they can be widely used in different types of industries. For example, in industrial catalysis, solar energy utilizations or solar cells, paint production, right? So people invented different types of paints also because these nanoparticles has very good light scattering properties. We also use these nanoparticles in sensors, tires, right? People put carbon black into the tires because they can increase the mechanical performance of these rubber, right? So, and these carbon black are actually made by just combusting the gasoline or basically the petroleum products, right? Because the petroleum products have very high carbon number in the reactant, right? During combustion, you form carbon black that is purely carbon or mostly carbon, right? So that's the process that give you the black color of these soot or carbon black nanoparticles because they have a lot of carbon in there, right? As we said, there are sunscreens, and nowadays we also use nanoparticles for water treatment and even for the control of the coronavirus, right? So during the pandemic, you also see all different types of advanced nanoparticles that can kill or disinfect these viruses, and they can be used on fabrics, right? So if we do that, then after the particles or after the virus or pathogens were collected by these fabric, they are automatically disinfected. So there are also some controversial applications, for example, by using nanoparticles in agriculture, right? You can probably see for some of the research, we can grow giant watermelons or giant tomatoes because we add in some nanofertilizers in there. But overall, by using nanoparticle or nanotechnology in agriculture, we may end up saving a lot of our resources. For example, phosphorus, right? So there's a study showing that if you just use the conventional fertilizer, then you actually waste a lot of phosphorus. And in the state of Florida, actually, the state of Florida is a major provider of the phosphorus fertilizer in the United States. But if you use these large chunks of fertilizers, they actually get washed away or they get accumulated into the river. So they can lead to some, let's say the dead zone, right? So that's putting too much nutrition into the water body, and then eventually they can have algae blooms, and then the algae get decomposed, and you get rid of the oxygen in the water, which is causing these dead zones. But by changing the application of this large quantity of phosphorus into the nanoparticle route, right, you can actually save a lot of these phosphorus, and then also improve the performance of the fertilizer and improve the productivity in agriculture, right? People actually show that nowadays we're generating these commodity nanoparticles at an annual yield of more than 2 million tons, right? And also by the end of 2020, which is already 3 years ago, the total let's say the industry represent a profit or represent a value of around 3 trillion US dollars. Okay, so as you can see, the aerosols can pose so many different impacts, right? It can influence our health, it can lead to climate impacts, it can affect air quality, and then it can also have a lot of good performance in our daily life once they're manufactured through these industrial reactors. But what determines these impacts? So we have to look into the intrinsic properties of these aerosols, right? So we can probably divide it just based on the major categories, which are physical properties, chemical properties, and biological properties, right? So that represents physics, chemistry, and biology. Okay, so what are the examples of physical properties? So the examples can be how large they are, what is the shape, right? What is, let's say, the volatility, viscosity, hygroscopicity. So basically, those are the physical properties that are not related to the chemical components. And in terms of the chemical properties, of course, the chemical composition is a major one, right? And then there's also the reactivity, which is related to the chemical component. For example, some of the aerosols can stay in the atmosphere for a long time. An example is that this year there's a severe wildfire in Canada, right? These wildfire-generated particles traveled over days and reach United States. And the northeastern was basically even damaged by these wildfire aerosols, right? People have to bring their mask again to reduce the exposure to these aerosols. So in the atmosphere, while these aerosols are being transported, they can also go through a series of reactions. And the most common reaction is that during the daytime, you have solar radiation, and a lot of these organic components become oxidized. Then they become less volatile and becomes more oxidized. Once they're inhaled by people, they can generate more potential, generate more reactive species, and becomes more toxic. And talking about toxicity, then that's related to the biological properties, right? So basically, these aerosols, once they are dissolved into water, they can generate reactive oxygen species, right? Commonly seen as these species that's causing different reactions or negative impacts onto our body health. But also, these aerosols can carry pathogens. And a few of the students in my class are actually working on these bioaerosols to try to understand how viable these pathogens are, right? Whether there are certain virus or certain type of bacteria in the aerosols and so on, right? So we need to do different types of analysis and use different aerosol instruments to understand their physical properties, chemical properties, and biological properties, right? And one example is the shape, right? As we know, these aerosols can have all different types of shape, and these shapes can really influence the health impact. For example, here is a soot, right? So the soot particles that are generated from the typical combustion engines or combustion processes, they have these chained shape, right? They're made of these primary particles, right? Generally in the 10s or 10 to 50 nanometer. And then they actually agglomerate. Basically, they form this neck here due to the high temperature process. And then we call this process as sintering, right? But at the same time, the residence time of these particles under high temperature is not long enough, so they cannot coagulate or sinter into a single particle. And that's why they have this chain-shaped like particles. And because of this chain shape, these aerosols or the soot particles are going to have a high specific surface area. So basically, their surface area per unit mass is going to be much higher. And if they have a much higher surface area, and then it means that they have more reactive sites, and once they're inhaled, they can lead to more toxic effects, right? And a lot of these organic species or sulfate species, they're going to retain these more spherical shape. But for the dust, or let's say the sea salt, they're going to show the more of a size that reflect their crystallinity, right? For example, the dust can have these irregular let's say the sharp edges, right? So recently, people are quite interested in the silica dust, right? For example, they are mainly encountered during the construction processes. Basically, the workers are exposed to the silica dust. And the silica dust normally have a very sharp edge. They're made of pure or crystallized silicon dioxide, right? Because of this sharp edge, once they're inhaled into our body, these edges can cut through let's say, the epithelial cells or the surface cells, right? And further lead to some health effects. The sea salt is going to reflect what the sea salt is made of. For example, if it's made of sodium chloride, then they're going to have these cubic shape. And sometimes people even need to consider this cubic shape when they are trying to form sodium chloride nanoparticles. So for example, if you want to calibrate your particle sizer, right? For example, the scanning mobility particle sizer, and then you are atomizing sodium chloride solution, then basically the mobility size that you measure by the instrument is not going to reflect the size of a spherical particle, right? It's because sodium chloride is going to retain a cubic shape. I mean, in terms of cubic shape, how do we relate that, or the physical size, to the mobility size, right? There's a correction factor that people have to apply to make sure that you're measuring the right size, okay? So then, for example, pollen, some biological aerosols, they're going to have some distinct microstructure or the shapes, right? So basically, these aerosols can have a wide range of size, shape, phase, and chemical composition, okay? So, and since we talk about size, I would say that the size distribution is the most widely used property to describe the physical characteristics of aerosols, right? So size distribution basically gives you the concentration of the aerosols in different size, or in different size bins, or at different size values. So people actually call different modes of the aerosols with different names, right? So, and normally if you measure the aerosol size distribution in our atmosphere, they are going to show different modes, right? They're not going to show the exact size in different mode, but typically you're going to show a mode in certain size bin, let's say from 10 nanometer to 100 nanometer, from 100 to, let's say, 1 micrometer, things like that. So we can name these different modes of the aerosol size distribution with different terms. For example, you can have the nucleation mode, which generally refers to aerosols below 10 nanometer, right? And then there can be Aitken mode, that is the aerosols between 10 to 0.1 micrometer, and between 10 nanometer to 100 nanometer. And then there can be accumulation mode from 100 nanometer to around 1 micrometer. But normally you'll see that below, let's say the mode is going to be below 500 nanometers. And there's going to be the coarse mode, right? Generally refers to the aerosols generally from, let's say, the large physical processes. For example, the sea spray or the dust blowing and so on, right? And these coarse mode aerosols are normally in the have a mode size of around 10 micrometer. So these are the four different modes that people encounter. And as you go to different subfields in the aerosol research, you're going to see, basically find more modes. For example, during the COVID-19 pandemic, people are trying to find out what is the size distribution of the human respiratory droplets, right? So on that topic, people have done so many measurements, and it seems that even for the human respiratory droplets or human respiratory particles, there can be different modes. For example, if the aerosols are generated from the deeper lung, right, from the alveolar region, or from the basically the bursting of the tiny bubbles in our deeper lung, then you are more likely to generate tiny aerosols, let's say below the size of 1 micron. But if the droplets are generated from, let's say, the upper respiratory tract, for example, the vibration of the, let's say, the human body parts, right, in the upper respiratory system, then you are more likely to generate larger droplets that are with a, let's say, with a mode size of around 10 to even 100 micrometer, right? So different mechanisms are going to generate aerosols with different modes. So here I'm trying to show you, let's say, even for the size distribution, although most of the time we represent the size distribution with the particle number as the y-axis, but sometimes we can also plot the size distribution based on different metrics, right? We can plot them based on the volume-based size distribution. The way to plot, or the way to calculate volume-based size distribution, is just to assume that the particles are spherical, or you can assume a specific shape, right? And then consider the shape effect on the aerosol size to the volume, right? But most of the time, we just assume it's spherical and has a certain density that we can assume. Well, this is about volume, so there's no density involved.
But you may also calculate the mass-based size distribution, right? So most of the time we're going to see a much higher number concentration of the nucleation mode and the Aitken mode aerosols. But if you're plotting them into the volume-based or even the surface-based size distribution, surface area-based size distribution, you're going to see the size distribution basically shift to the right. And this is mainly because the smaller particles are not going to play a major role in calculating the volume, because the volume is proportional to dp to the third, right? So if you have a particle of 1 nanometer and a particle of 10 nanometer, then their volume is different by 1,000 times, right? And because of that, the larger particles are going to play a more important role when you're trying to calculate the volume or mass-based size distributions. And the size distributions can also vary based on their locations. And that's why people host so many campaigns at different locations of the world to understand the aerosol properties and understand their impacts onto the human health or the climate. So this is an example showing the aerosol number-based size distributions at different distances downwind Los Angeles City. Right, so this is 30-meter downwind, 60, 90, and 150-meter downwind. So you can see that as the particles are getting transported or getting mixed, right, their size distribution can also shift. So at the first, you may see more, let's say, nucleation or Aitken mode aerosols, but as the aerosols further get transported, there may be some chemical or physical processes. For example, the physical process can be dilution, or there can be the dilution or dispersion, right? Or diffusion of the very tiny particles can shift their size distributions. But also there can be chemical processes where, for example, if this is about aerosols generated from, let's say, the traffic, then while the aerosols are being generated, there are also a large amount of volatile organic compounds. And these volatile organic compounds can condense onto existing aerosols, and then they can make their size a little bit larger and also broader, right? And also the aerosol size distribution really depends on where, let's say, what altitude you're trying to measure, right? So most of the time, people live in the troposphere, right? So the air in the troposphere, especially in the boundary layer, is relatively well mixed. So boundary layer, I'm just talking about within an altitude of around hundreds to 1,000 meters, right? So normally you're going to see a much higher concentration of aerosols in the boundary layer because that's where most of the emissions are generated. But as you further lift up, right, to the free troposphere, then you're going to see a much lower concentration of aerosols, but also you're going to see more nucleation mode aerosols. And this is mainly because at higher altitudes, you're going to have, so one condition that creates or prefers new particle formation is cleaner environments, right? So basically you don't have a large number of aerosols that eat up all of those gaseous vapors that form new particles. So also the temperature is lower, right, in the higher altitude, and then there's stronger solar radiation, right? So they can oxidize some of the species. For example, sulfur dioxide, they can get oxidized into sulfuric acid, and sulfuric acid can directly nucleate and form tiny particles. So basically, in the free troposphere, there are going to be a stronger new particle formation processes compared to the troposphere, let's say, compared to the boundary layer condition. All right. And then the concentration overall is also lower. So here you can also see the surface area based size distributions and then the volume based size distributions. So briefly about the chemical composition, we're going to talk a little bit more about these later on in our class. So basically, you can categorize them into refractory species. So basically, the species that cannot be easily broken down. They can include the metals, for example, different types of heavy metals or noble metals, right? And there can also be elemental carbon. So elemental carbon is really difficult to break down because they're just made of pure carbon, right? So examples, let's say the metals can be coming from the mining or let's say from the typical combustion process too. And one example is mercury, right? Whenever we burn coal, there's going to be some mercury getting generated, and including and also lead, right? So the elemental carbon is also coming from the combustion process, but there can also be refractory species. So these are non-refractory species, basically means that they're too stable to be broken apart. There can also be refractory species that includes organics. So organics, you can also divide it into primary organics or secondary organics. So we're talking about aerosols, right? So these organics are not volatile species anymore. So they're already basically forming tiny particles. So primary organics can be those, let's say, coming from the car engines, right? You generate a lot of volatile organic compounds inside the combustion condition, and once they're emitted into the atmosphere, there are already some organics that are forming aerosols, right? So they exist in the form of the aerosols. There can be secondary organics. So the primary and secondary really means that when they're being emitted, are they already formed as aerosols, or they're formed through a different different chemical processes after they're formed? For example, in the forest, so we know that the trees can emit a lot of volatile organic compounds. For example, the alpha pinene, or the let's say the isoprene, right? So these isoprene gas molecules, they can react under the solar radiation, get oxidized, and then they can nucleate. For example, they can react with the sulfur dioxide or sulfuric acid, and then further form particles, right? So these particles are made of organics, but they are not directly emitted by the tree. So that's why we call these as the secondary organics. So from the forest, this is just one example. They can also get formed from other process that's happening in our nature. So there can be sulfate, right? So sulfate, a major I would say a very significant emission source of sulfate, or is basically from the industrial process, right? So whenever we burn fossil fuel, there's going to be tiny amount of sulfur in there. But in terms of sulfur, once they're emitted, they're formed into sulfur dioxide. And then in the atmosphere, they're oxidized into sulfuric acid. And sulfuric acid has a very low volatility, which means that they're ready to form nanoparticles. They're not going to exist in the form of sulfuric acid vapor, right? They can directly condense onto existing particles, or they can form particles by themselves. So that's why the sulfate is playing a quite important role in the aerosol chemical composition. So there can also be ammonium. So ammonium, so from the human activities, from the fertilizers, but there are also natural process, for example, lightning process, right? It's the same for the sulfate. So over the ocean, there can be some biological properties that form the sulfate, and then they're in the form of dimethyl sulfide, or DMS, right? And then they can basically sustain the aerosol number, or the aerosol production over the larger ocean surface, where you don't really need human activity to get involved to form tiny particles, okay? So this is a study that's showing the aerosol chemical composition in different locations on our Earth's continental area, right? So different type of aerosols are represented in different colors. So by convention, sulfate is shown as red, right? Nitrate is shown as blue, ammonium shown as yellow, and then chloride shown as purple. And then for the organics, they're shown as green, right? So for this study, they further divide the organics into different types of different oxidation status. For example, you can have the low volatility OOA, right? So these are the oxygenated organic aerosols, right? There can be total OOA and the semi-volatile OOA and other types of organic aerosols. So you can see that for different locations on our continental area, the sulfate and organics are taking a pretty significant composition on the aerosol in terms of aerosol chemical composition, right? The sulfate organics are most of the time the most important chemical composition in these aerosols. And when you're talking about aerosols, let's say formed in the urban area or formed in the remote area, then their detailed chemical composition can be different. For example, if you're talking about the let's say the forest in Finland, right? So this should be the Hutiala station in Finland, right? So you can see their organics are going to occupy a larger fraction in the aerosol chemical composition. But if you compare that to the urban area, then sulfate is going to provide more chemical composition, right? As we know, our Earth is most of the area is composed of or is covered by the ocean, right? So what about over the ocean? Because there's no human activity on the water, right? So are there aerosols getting generated? As I introduced earlier, the ocean has its own biological cycles that can basically provide these dimethyl sulfide. And currently, this is one of the proposed mechanisms. There are also other mechanisms being studied that basically form aerosols over the ocean, right? So, and also, as we know, the sea spray or the ocean spray that generate aerosols during the breaking of the waves or during the bursting of the bubbles can also generate aerosols. And actually, that process generates most of the aerosols in terms of mass, right? Because normally they generate sea salt aerosols in the size of micrometers, and they contribute more mass to the aerosols. So this is a measurement at Mace Head. That's the west coast of Ireland, basically the east side of the Atlantic Ocean. So people looked into the chemical composition of aerosols that were collected at the Mace Head. And you can see during the low biological activity process, most of the aerosols are just made of sea salt, right? So sea salt, they can be made of some chloride, sodium, magnesium, and then let's say the sulfate, and then some organics over there. So these organics can either get transported from North America, or there can be some composition that are generated from these biological processes, right? But under the high biological activity, basically when the northern hemisphere is in the summer, right? So temperature is higher, there can be more biological activities, let's say in the ocean or also near the coastal region, right? So then you are going to see more organics, right? And also sulfate getting generated. So here, WSOC means water soluble organic compound. WIOC means water insoluble organic compound or organic carbon, right? So basically, the aerosol composition is also affected by the activity or the biological activity over the ocean. Okay, so finally, it's about the biological aerosols or bioaerosols. All right, so bioaerosols can get generated from our nature itself, right? If you go to the forest, you can basically inhale aerosols from all different types of sources or with different properties. So they can include the plant debris, pollen, bacteria, viruses, fungus, and algae, right? So there's one study actually suggests that the bioaerosols may be a large source, let's say. So basically their emission quantity may be as large as the dust or sea salt on our Earth, right? So they are generated from in a large quantity. And so as we know, for the past few years, we have focused a lot about aerosols or pathogens, right? Basically the viruses or pathogens coming out of the patients. And some of you actually work on these projects trying to sample these viable viruses, right? And also to prove or to find out what are the transmission mechanisms of these diseases, okay? So this is a brief overview or a brief introduction of this class. So we're going to focus on basically the instrumentation to conduct all different types of measurement in terms of physical, chemical, and the biological properties of these aerosols. So finally is some logistics of this class, right? So this is about the grading policy for our class. So as you can see, we don't have a final exam, right? The final exam is replaced by this project, and you're going to form a written project and also basically written report and also a in-class presentation. All right. So there's going to be homework, midterm exam, and the midterm exam is mainly going to cover the physical property characterization and also some I think a little bit about the chemical composition characterization. So also there's going to be an in-class quiz or several in-class quizzes where this 5% or the extra 5 points will be the bonus of your class. All right. So finally, this is a course schedule or the tentative course schedule of this class. So I will be away or basically unavailable for some of the classes because of the meetings. For example, the triple AR meeting at the beginning of October and also the ASCHE meeting. But during those times, we may skip 1 or 2 classes, or we may also just upload a recorded lecture, so you guys can basically listen to what's happening and also continue the learning in this class, right? Okay, so that's it. So I look forward to having a fantastic and also exciting semester with all of you guys. And just let me know if you have any questions. Okay, see you next time.